So lecture 6 part 2, still in chapter 3. The topics for this will be intramodal dispersion, intramodal dispersion in optical fiber. So somehow we are still in the dispersion topics, So if you can recall from lecture 6 part 1, yesterday and also last week lectures, the topics that we have learned is intermodal, intermodal dispersion. Okay, sorry for this. Right, so for this, we're going to learn about the intramodal. So somehow it's a bit different in terms of the concept. So I need you to understand the concepts very well because it is very important for us later when we design the optical communication system, Okay, so this will be the content for today's lecture. In which we're going to learn about the factor number 2 of dispersion, which is intramodal dispersion. And this intramodal dispersion can be further divided into two types. The first one is what we call as material dispersion, and the second type is waveguide dispersion. Okay. Okay. Assalamualaikum, Mustafa Muhammad. Mustafa, can you hear me clearly? Hello, Mustafa. Okay, can we have a conversation then? You can on your speaker. Okay, Mustafa. Hello? Mustafa Mahmoud?
Yes, doctor.
Oh, okay. I noticed that you have not come to my class for a few weeks. What happened to you?
Sorry, I had a car accident. I was in the hospital.
Correct, but it's not a good excuse not to come to the class. Do you have any... You're still in hospital or you have been discharged from the hospital?
No, I have been discharged.
So you're in Malaysia or outside Malaysia?
Yes, I'm still in Malaysia.
Okay then. Okay, so good to hear from you. Yeah, I thought you have dropped the subject. Okay, let's go back to the class, to this content of lectures. Okay, sorry for that. Yeah, sorry for the interruption just now. Okay, so again, there should be two main topics for the dispersion, intramodal, material, and also we've got dispersion. So we're going to cover this dispersion type in detail, and followed by examples. So hopefully we can finish these topics by today. Okay, let's proceed with this intramodal dispersion. So intramodal dispersion is also known as a chromatic dispersion. So there are two names for intramodal dispersion. Either we can call it intramodal or we can also call it as chromatic. Chromatic dispersion. Okay, so this chromatic dispersion occurs in all type of fiber, which include the single mode, the multi-mode, and also grain of step index type. So as opposed to intermodal dispersion that we have learned before this, intermodal, intermodal is only severe or observed in a multi-mode fiber type. Multi-mode fiber type, both step index and also graded index, the grain. But for the chromatic, we're going to have it in both single mode and also multi-mode fiber. Okay, so these are the things that you have to understand very well. Okay, and the optical pulse broadening, because we know that the effect of dispersion is to broaden yeah, or spread the pulse width, yeah, the pulse width. So basically, this broadening of optical pulse due to this chromatic dispersion is actually resulted from the spectral line width of the optical source. Okay, what is meant by spectral line width? We're going to discuss about spectral line width after this, but we can say that the dispersion due to this chromatic basically is due to finite spectral line width of the optical source, in which if you can base on this diagram, okay, this is basically a pulse from the laser, yeah, a pulse from the laser, and we can say that for the laser source, there exists a line width. So delta lambda here is the line width, which is produced by the optical source. Yeah, produced by the optical source, in which the delta lambda is measured at the half power of the peak. Yeah, half power of the peak. So the peak is 1 dB, so it should be measured at 0.5 dB. So that should be the line width, the spectral line width of the optical source. So we can see that for this particular spectral line width, we notice that there should be a lambda range, right? There should be a lambda range, yeah, a lambda range at this particular intensity of light. So it can be said that this pulse broadening due to this chromatic dispersion is basically due to wavelength, or I can say numbers of wavelength values which are said to be propagating or propagated inside the optical fiber. Okay, so that should be the line width, yeah, the delta lambda. Okay, so basically there should be two mechanisms, as I mentioned before. The first one is a material dispersion, yeah, in which this type of dispersion is due to different wavelength components, the delta components, that travel at different speeds in optical material. Okay, and the second type of dispersion, which is waveguide dispersion, is due to the light energy of a mode, which is said to be propagating in both core and the cladding region. Okay, and we can say that this can be regarded to the power distribution in the core and the cladding region. Yeah, and this power distribution will be depending on the lambda. So if we can base on these two dispersion type, both material and waveguide, this dispersion will be heavily dependent on the lambda. Yeah, dependent on the lambda. That's why, as I've stated here in the first statement here, that the pulse broadening or the pulse spreading in chromatic dispersion is basically due to this spectral line width, or due to these different wavelength components or different wavelength values of your optical source. Okay, so that's the idea. Yeah, that's the idea of chromatic dispersion or intramodal dispersion. Before we proceed further, so you have to understand this very well. Yeah. So material dispersion and waveguide dispersion, both of it are due to different wavelength components exist in your power source. Yeah. Okay. So we go for the first one, which is a material dispersion. Okay, so material dispersion is caused by different wavelength traveling at different speed. Okay. So as we have learned before this, yeah, we can refer back to the previous slide. So this is your power source, yeah. Your power source are like a spectrum. Yeah, we have a line with the delta lambda there. So we have numbers of wavelength which will propagate inside the optical fiber. So due to these wavelength values that propagating in the optical fiber, we are going to have a different speed, or we can have different wavelength which is going to travel at different speed in your optical fiber. Okay, so we can relate these conditions, yeah, and we can recall from this equation, yeah, V is the speed of light in the optical fiber, C is your speed of light in vacuum or in free space, and N is your refractive index. Yeah, so from this equation, we know that the refractive index of material will be depending on the lambda. Yeah, will be depending on lambda, or it can be said that N Yeah, n will be depending on lambda, because different lambda will be having different group velocities. Yeah, so as such, when we have different lambda with different n, so when we substitute these ideas into this equation, we can have different n will give us different velocities, right? Different n will give us different velocities as a result of different lambda just now. So we're going to have multiple velocities in our optical fiber. So these velocities is the group velocities that we have learned in lecture 6, part 1 before this. So I hope that you can still recall the difference between the phase velocities, the Vp, and the group velocities, the Vg. Yeah. Okay, I repeat again for these ideas. So due to different lambda that will travel in your optical fiber, yeah, and I hope that you understand why we have different lambda because of the spectral line width of your optical source. Okay, so for different lambda, we're going to have different n, and as a result of different n, we're going to have varieties of group velocities that will propagate in your optical fiber. Okay, so this difference of group velocities will then give rise to this material dispersion effect. Okay, so I hope that you can relate the idea of what triggering or what causing this material dispersion in your optical fiber. Yeah. Okay, so so as mentioned before, the effect is due to this finite spectral line width of the optical source, and the spectral line width or the source line width. There should be two names there. Again, the same things. Basically, is the range of the wavelength which is emitted by the optical source, yeah, lasers or LED. So lasers and LEDs are two types of optical source, yeah, and we're going to learn this in detail in chapter 4 next week. Okay, so I repeat again, for this spectral line width or source line width, that should be the range of wavelength which is emitted by the optical source, and basically in order for us to combat the material dispersion, our interest is to have a smaller line width, yeah. Because if we have smaller line width, we're going to have lesser wavelength that will travel in our optical fiber, and as such, the velocities or the group velocities will be reduced in optical fiber. Okay, so from this statement, if we have smaller line width, we're going to have smaller spread in wavelength. So you know about this, yeah? And the things that we can say that the source is more coherent, yeah? So coherency of the source is depending on the line width value. If line width is reduced or small, so the source is said to be more coherent, yeah? More coherent. Okay, so this is a typical line width or spectral line width for your optical source or light source. We have LED here. So it's about 20 nanometer to 100 nanometer. So it's very big, yeah, line width. That's why LED will not be used in long distance application, yeah, because it will induce a very huge material dispersion. Yeah, we can see from this value, we have a very huge line width. So huge line width will cause a severe material dispersion. Yeah. Okay. And for the semiconductor laser diode, is very small, 1 nanometer to 5 nanometer. Yeah. So for long distance application where we want to reduce the dispersion, for sure, laser diodes will be applied, yeah, will be used at the optical source. Okay, then we also have solid state lasers. We have 0.1 nanometer, and we also have Heine gas lasers, here neon, gas lasers about 0.002 nanometer. Okay, so this is a typical line width for the optical source, yeah. Right. Okay, so this is a graphical figure to explain the material dispersion effect. Right, so we see that this is our single mode fiber having a length of L. We have the input pulse and we have the Bourdon pulse once it exits the single mode fiber. Okay, so we assume that in your optical source, optical source, we are having a range of wavelength that will be produced or that will be coupled in your optical fiber, in which the range is from the blue light. Let's say we assume a visible spectrum, yeah. We have a blue light, yeah, and this is the wavelength for it, which is lambda naught minus delta lambda divided by 2. We have a green and we have a red. Yeah, so this is a difference of your wavelength that will be coupled. Yeah, that will be coupled in your optical source. So allow me to get back to the previous slide. Yeah, this is the case now. Yeah, that basically that diagram is related to this diagram here. So when we have the line width that is traveling in your fiber optic structure, there should be a red light at certain wavelength. Yeah, we have a green light at lambda naught, and we have blue light at this wavelength. So we assume here this red light is at the wavelength of lambda naught plus delta lambda divided by 2. Yeah, because the line is delta lambda. So here we should be delta lambda divided by 2, and here should be negative delta lambda divided by 2. That's why for the red light, the wavelength is located at lambda naught plus delta lambda divided by 2. And for the blue light, it is lambda naught minus delta lambda divided by 2. Yeah. So that's why we have this value for the wavelength. Yeah. So this will be the wavelength that is said to propagate in your single mode fiber. Okay. So once it enters the single mode fiber, and we know that from what we have discussed before this on the principle of light, yeah, since you have different wavelength, so different wavelength will induce different group velocities. Yeah, so we have learned this. So different group velocities will then affected on the time delays. Yeah, time delays, because we know that the light will travel at the same distance. Yeah, same distance, but due to different group velocities or different velocities, the time will be different, right? Because we know that velocities is distance divided by time. So distance is constant, velocity is different, so time will be different. Yeah. So as a result, we're going to have a time delays due to these different wavelengths transmitted, and we can notice that we're going to have a red laser, a red light, which will arrive first, followed by the green light, and then followed by the blue light. So as a result, we're going to have a effect of broadened pulse or dispersion effect that will take place in this particular case. Yeah, right. So by this diagram, hopefully you understand the effect of a spectral line width of the optical source that will produce a dispersion or metal dispersion in your fiber optic structure. Yeah. Okay. This is what I mentioned here, that the pulse spreading or pulse broadening is caused by propagation through dispersive material. Yeah, so this is what we call as a dispersive material, because different lambda will give different n. Yeah. Okay. Right. Okay. So now we come to the mathematics. Yeah. So we have understand the concept very well. So we are now we're going to get the equations that shall be used to explain or to describe the metal dispersion phenomena. Yeah. Okay. So we have two cases here. We assume that we have a path or the length of optical fiber, which is a length of L. Okay, and we assume that that is a tau. Tau will be the time that will be required for a pulse to travel along L distance. Okay, so for this we can just say that the travel time per unit length will be tau or divided by L. Yeah, yeah. So tau divided by L is the travel time per unit length. Okay, so when we consider a case of non-dispersive medium, so non-dispersive medium means that there should be no effect on the lambda. Yeah, means that if we have different lambda, there should be no difference on the time taken, in which this is somehow not exists in the real world situation. Yeah, yeah, but this is for the sake of discussing the metal dispersion, so we have to consider also. Yeah. Okay, so for a case of non-dispersive medium, we can say that the time travel per unit length will be a constant. Yeah, it will be a constant for all lambda values. So it does not depend on the lambda. Okay, it does not depend on the lambda. So we can say that due to this, the change of n with regard to lambda will be 0. D squared power of n divided by d lambda squared will be 0. Means that the change of refractive index n with regard to lambda will be 0. For a dispersive medium, we cannot get these ideas because we know that the n is depending on the lambda, right? N is depending on lambda. So for that particular case, the dn of the lambda will not be 0, supposedly. So that's why for a case of dispersive medium, which is a real world situation, the d squared n over the lambda squared will not be equal to 0. As such, we're going to have a case whereby when we have two different lambdas here, okay, let's say we have a lambda 1, the time taken for the pulse to travel will be tau per L 1. This is a time taken for the pulse to travel for a length of L when we have the lambda of lambda 1. And if you have the lambda equals to lambda 2, so the time travel will be different. So it is now located here, which is tau divided by L subscript of 2. Okay, so we can see that when we have a difference of lambda here, we also have a difference of time taken for the pulse travel. Yeah. So hopefully you get the difference here. Yeah. Okay, I repeat again. When we have a light having a lambda 1 wavelength, the time taken for the pulse to travel for a distance of L is symbolized as tau over L1. And if we have a light having a lambda 2 wavelength, the time taken will be tau over L2. So we notice that for this difference of lambda, which is notified to be the delta lambda, we are supposed to get a difference of time travel, right? A difference of time travel. So this difference of time travel is what we call as a pulse dispersion. Yeah, pulse dispersion or pulse spreading per unit length. Okay, yeah. So this is mathematical explanation of this diagram. Yeah, this diagram that we have here. So mathematically, it is discussed like this. For the case of dispersive medium where the refractive index will be depending on the lambda. Okay, so let's say, that's why we put it here that for a non-dispersive medium, which is for this one, which is not exist at all, the travel time is independent of wavelength, yeah? But for a dispersive medium, yeah, for this particular case, dispersive medium, travel time for lambda 2 is higher as compared to lambda 1. So evidently shown by this, yeah. Lambda 2 travel time is higher than the lambda 1. And the time difference between these two wavelengths, which is delta tau over L, is what we call as a pulse spread per unit length, yeah? Pulse spread per unit length, which is a difference between tau over L subscript 2 minus tau over L subscript of 1, yeah? So this is what we call as a pulse spread per unit length. Okay, right. Okay, and from this figure B, if I can refer back to this, yeah, from this figure B, we can also write that a tau over L delta. So this is I can say a slope, yeah, a slope of this line, yeah. Sorry, a slope of this line. Okay, a slope of this line is written to be tau over L prime. Okay, so it is equal to a delta tau divided by L divided by delta lambda, yeah. Because we can assume that this is a straight line here. We can assume a straight line. So a slope of this line will be a delta tau divided by L divided by delta lambda. Okay, so we're going to have this equation. And this can be manipulated to give us delta tau over L will be tau over L prime multiplied with the delta lambda. Okay, and I'm not going to cover in detail on this equation, but it can be obtained that the tau over L prime basically will be negative lambda over C d squared n over a d lambda squared that should represent this tau over L prime. And if we substitute equation 2 into equation 1, we're going to have this equation here. Yeah, where a delta tau over L, which is a pulse spread per unit length. Yeah, pulse spread per unit length. Basically, it's the same as this, yeah? Same as this one. Okay, same as this one. So delta tau over L, which is pulse per unit length, is equals to this equation number 2 just now, which is tau over L prime, negative lambda over C d squared over d prime squared, multiplied with the delta lambda. So delta lambda is your spectral width, yeah, spectral width of your light source. Okay, so this is the equation that shall be used to calculate the pulse spread per unit length in nanosecond per kilometer due to material dispersion. Yeah, due to material dispersion. Okay, any questions so far on this uh, on this topics of material dispersion?
So far, no, Doctor.
So
No,
far,
doctor.
yeah. Okay, good. Allow me to get back to the Google Meet window because I think some students trying to get in the class just now. Nobody. Never mind. It's okay. Oh, okay. Okay. Let's get back to this slide. Okay. Hopefully by now you have understand about material dispersion, how we obtain up this equation that enable us to calculate the pulse spread per unit length as a result of material dispersion. Okay. So this particular equations here is also termed as material dispersion parameters. Yeah, these equations here is also termed as material dispersion parameters. I'm going to learn this in the next slide here. Yeah. Okay. So like what we have learned in lecture 6 part 1 before, we noticed that there are two types of this. I mean, we have intermodal dispersion, but there are two conditions. Yeah, the first one is when we assume that there should be no overlapping in the pulse, and the other one is based on the overlapping pulse, where we consider that to be a statistical method, a Gaussian method, yeah, or RMS value. So the same things apply here for a material dispersion, where we can also obtain the RMS value of the pulse broadening or pulse spreading by this equation. Yeah, in which if we consider the RMS value of a delta lambda to be equal to this sigma lambda. Okay, so it can be shown that the RMS pulse spreading due to this material dispersion, we can write this as this equation. Yeah, sigma m will be equals to sigma lambda, which is your RMS value of your spectral width multiplied by the length of the optical fiber divided by c, speed of light, and this is your material dispersion parameters. Okay, lambda over c lah, yeah. And we can also rewrite this equation simply to be looked like this. Sigma m, yeah, which is RMS pulse spreading or pulse broadening, equals to dm. Dm is material dispersion parameter as stated here. L is the length of the fiber optics, and sigma lambda is the pulse. Is the RMS spectral width. So dm is equals to lambda over c d squared n over d lambda squared. So if we compare these equations here that we have, this is for the case of RMS value, yeah, RMS pulse spreading. And this is the equation for the case where we consider non-overlapping assumption. So basically it's the same. It's the same equation basically. We can see that if we take L to the right hand side, yeah, this L is taken to the right hand side, we're going to get delta tau shall be equals to, this is your dm. Yeah, dm is the material dispersion parameters. Dm multiplied with delta lambda multiplied with L. So basically, this equation and these equations are the same. The difference is the second equation here is to be based on RMS value of the spectral line width or spectral width, and also RMS value of pulse spreading. Okay, right. Right, yeah. So hopefully you understand this clearly. Okay, so we know that our fiber optics, most of these fiber optics for commercial application is to be based on pure silica, pure silica. Okay, so this is the case that explain about dispersion or material dispersion effect in your pure silica. Okay, we notice that there should be a zero dispersion value in which there should be no dispersion in your silica at this wavelength, a single wavelength of 1276 nanometers. Yeah, so this is obtained from the experiment done by this manufacturer, and they found out that zero dispersion wavelength for a silica-based fiber will be obtained at this wavelength. Yeah, a single wavelength of 1276 nanometer. So above 1276 nanometer, your material dispersion parameter dm, so this is dm just now, yeah? Sorry, I forget to put the dm there. There should be m, which is your material dispersion parameters. The value will be bigger than 0 given by this line. And for lambda, which is less than this 1276 nanometer, the dm will be less than 0. Okay, that should be the case. Yeah, this is a diagram, a figure which is obtained by the manufacturer, which states that zero dispersion wavelength for the pure silica can be obtained at this wavelength of 1276 nanometers only. Yeah. Okay, so this is from the diagram. It is stated that the dm will be 0 at this wavelength, which is called as zero dispersion wavelength. Okay, and further on, dm is negative for lambda lesser than lambda zd and positive for lambda bigger than lambda zd. Okay, so what is meant by negative dm? So negative dm means longer wavelength is said to travel faster than shorter wavelength. So this is understood, and it is shown here in this diagram just now. Sorry, okay, this you have to refer back to this. This is longer wavelength, a shorter wavelength. So longer wavelength will arrive first, followed by the shorter wavelength. Okay, but for the case of dm positive, we're going to have a shorter wavelength which will travel faster than longer wavelength. Yeah, this is for the case of a positive dm. Right. So this is a special formulation which can be used to calculate the material dispersion parameters, which is based on this equation, based on this diagram basically, in which for a pure silica, the dm is written to be 122, 1, yeah, this is 1, minus lambda zd divided by lambda. Okay, so lambda zd is known to be at this location, which is 1276 nanometer. So by this equation, we can obtain the value of material dispersion parameter dm at any wavelength value. Yeah, at any wavelength value. For instance, let's say you want to find out what should be the value of dm at 1550 nanometer. So simply what you have to do is you have to substitute lambda zd as 1276 nanometer, lambda as 1550 nanometer, and then you're going to get what should be the dm. Yeah, what should be the material dispersion parameters for the case of pure silica. So this equation is only valid if your fiber optic structure is made of pure silica or fused silica. Yeah, so the unit for the dm is picosecond, yeah, picosecond, which is power of negative 12, divided by nanometer kilometer. So nanometer is the spectral line width, yeah, and kilometer is the distance. Yeah, that's why when we refer back to this equations here, I wrote this equation. This is your dispersion in picosecond. The dm is in picosecond nanometer per kilo, picosecond per nanometer kilometer. L is in kilometer. Sigma lambda is in nanometer. That's why when we multiply all of these three, we're going to get only the value of dispersion in picosecond unit. Okay, hopefully you understand this clearly. Okay, so let's have a look at this example on material dispersion. Yeah, I'm hoping that by this example, you can understand the material dispersions clearly. Yeah. Okay, so number one, we are having a material dispersion in optical fiber, which is defined by this difference of n with regard to lambda, d squared n over the lambda squared, which is 4 times 10 power of negative 2 micrometer squared. Estimate the pulse broadening per kilometer due to material dispersion within the fiber when it is illuminated with an LED source with a peak wavelength of 0.9 micrometer and RMS spectral width of 45 nanometer. Okay, so basically, you need to find out what is the value of pulse broadening per kilometer, yeah, which is basically due to matter dispersion. When we have an LED source with this peak wavelength, 0.9 micrometer, and your RMS spectral width of 45 nanometer, yeah. Okay, so as what we have learned before from the previous slides, there are two values for the pulse spreading due to matter dispersion. The first one, when we consider non-overlapping assumption, and the second one is due to RMS, yeah, RMS value or statistical value of your spectral width. So for this question, since we are given straight away that we are having RMS spectral width of the light source, so this pulse broadening that need to be obtained is the value of RMS, yeah, RMS pulse broadening or RMS pulse spreading per kilometer. Okay, so hopefully you understand these ideas, yeah. So let's have a look at the solution for this example number 1. Okay, okay, so this is the solution for example 1. So we are given these equations, yeah, d squared n over d lambda squared, which is 4 times 10 power negative 2 per micrometer squared. This is your lambda, wavelength of operation 0.9 micrometer, and your RMS pulse, so your RMS spectral width is 45 nanometer, yeah. Okay, but these equations alone or these parameters alone cannot be used to determine the material dispersion parameters, because we know that in order for us to calculate the RMS pulse broadening, we need to know the value of dm, right? So dm must be known before we calculate the RMS pulse broadening. So we need to find out what should be the dm. So if we base on this equation, we cannot use it to find, we cannot base, we cannot have this equation, or we cannot use this equation straight away to be used as your dm, because we know that dm is written to be like this, yeah, lambda over c with this multiplication of d squared n over d lambda squared. Okay, so since we know that this is the equation for the dm, we can use these parameters given, but have to be multiplied with the lambda and also divided by the c. So by this, you can then obtain the dm. Okay, so the lambda is 0.9 micrometers given. C straight away is 3 times 10 power of negative, sorry, 3 times 10 power of 8. Yeah, but I'm using 5 here. Why? Why 5? Because straight away I can use the unit of the speed of light to be in kilometer. Yeah, kilometer per second. Yeah, because end up knowing that the unit for the dm is picosecond per nanometer per kilometer, right? So straight away I can change this to kilometer per second, yeah? 3 times 10 power of 5, yeah? Okay, so your dn, your d squared over d lambda squared, this parameter is 4 times 10 power negative 2, and since we have micrometer power of 2, so this is the substitution for micrometer squared of 1 times 10 power negative 12. Okay, and further on, we're going to have this 0.9, yeah, 0.9, and this micrometer value can be cancelled out. Okay, but to obtain the nanometer, so that equation or this value shall be now substituted to be 1000. Yeah, that's why we have a nanometer unit there. So end up, your dm should be 120 per picosecond per nanometer per kilometer. So that should be your dm obtained from these parameters of d squared n over d lambda squared. Okay, any question on this? Yeah? On these solutions? I repeat again. No, yeah? Please clear. I repeat again, just for the sake of understanding. This is in micrometer, so I put it in meter now because micrometer, so in meter. So this is in kilometer. Okay, this is 4 times 10 negative 2. So 1 times 10 negative 12 in meter. So this value and this value can be cancelled out. So what we have here basically is in micrometer. Yeah, but we need to convert it into nanometer. So that's why we have 1000. Okay, so that's why the unit is picosecond per nanometer kilometer. So the dm is 120. Okay, so from the obtained dm, you can use it to calculate the pulse broadening per kilometer. So this is the equation. Remember, sigma m equals to dm multiplied with L, a distance, and the sigma lambda. Yeah, sigma lambda is a spectral line width. So since we need to find out the pulse broadening per kilometer, so L is taken to the left hand side. So we're going to have dm multiplied by sigma lambda, which will give us 5,400 picosecond per kilometer, or 5.4 nanosecond per kilometer. So this is your RMS pulse broadening per kilometer. Okay, so from this example, the idea is when you want to find the pulse spreading, the things that need to be obtained first shall be the dm. Yeah, the dm is very important for us to calculate the pulse spreading due to material dispersion. Yeah. Okay, so let's have a look at this next example. Okay, we have a glass fiber which exhibit material dispersion given by this equation or this term lambda squared and d squared n over d lambda squared of 0.025. Determine the material dispersion parameter at a wavelength of 0.85 micrometer and estimate the RMS pulse broadening per kilometer for good LED source with RMS spectral width of 20 nanometer at this wavelength. Okay, so somehow this problem is quite similar to the above one. The difference is only on these parameters given. Before this, you only given this, yeah, but now it's given to be in lambda squared multiplied with this squared over d lambda squared. Okay, so I believe that from these parameters, you can use it to find the dm. Yeah. Yeah, you can use this to find the dm. You are given the wavelength of operation is 0.85 micrometers. So you need to find out the RMS. Okay, so straight away it's RMS pulse broadening with the RMS spectral width of 20 nanometer. Okay, so let's have a look at the solutions, yeah, for this example. Okay, so this is the case, the solution for that example then. We're given these parameters, but this is not enough for us to calculate the dm. We need to have a c, right? C, yeah. So given lambda squared, d squared n over d lambda squared of 0.025. So knowing that the parameters dm is lambda over c. Okay, this is the equation for dm, lambda over c, d squared n over d lambda squared. So to use these parameters given, what we have to do is that we have to multiply these parameters with 1 over lambda c, such that when we multiply the parameters with 1 over lambda c, we're going to get back this dm, right? Because this lambda squared and this lambda can be cancelled out, so left only with lambda over c. So it will be similar to this. So simply we can just multiply 0.025, which is these parameters given, with 1 over lambda c, which is 0.85 micrometers of lambda, and c as the speed of light. Okay, so end up when we solve for this, we're going to get the dm will be 98.1 picoseconds per nanometer per kilometer. Okay, note that what I did here is that I straight away changed from 3 times 10 power of 8 to 3 times 10 power of 5 kilometer per second. And this micrometer unit is now changed to 850 nanometer. So that's why we have, this is the equation or the units for the dm, yeah, which is 98.1. So if you wrongly substitute the value, so this unit will be different, yeah. So you have to be very careful on the substitution of these values. Okay, so once you have this dm, you can obtain the sigma m or RMS pulse spreading from this equation that we have learned before. Yeah, so we need to find out the pulse spreading RMS per kilometer. So we need to bring the L to the left hand side. So sigma m over L, we're going to have 98.1 multiplied with 20 nanometer. So end up your pulse spread RMS per length will be 1.962 nanosecond per kilometer. Okay, so straightforward, yeah, straightforward. But you need to be very careful on the units, yeah, on this calculation of the DM, and subsequently on the calculation of RMS power spreading. Yeah? Okay, let us proceed with more example. Okay, number 3, we are given a case of a DM of a germanium oxide dope fiber, GeO2, germanium oxide dope fiber, to be 110 picoseconds per nanometer per kilometer at a wavelength of 860 nanometer. Okay, so this is quite straightforward because we are given the DM straight away, and the DM is given. Okay, we are given the wavelength. We need to obtain what should be the RMS pulse broadening per kilometer due to material dispersion if your spectral width of 40 nanometer with the output wavelength of it. Okay, I think somehow this is easier than before. Yeah, because we just substitute the value. Yeah, the DM is 110. Your sigma lambda is 40 nanometer. So by multiplication of this, you're going to get the RMS pulse broadening per kilometer. Okay, I don't think I have to proceed with this. So you can refer to the solution in the the solution file that will be given to you after the class. Yeah, you can refer to the solution file later on. Okay, so I'm going to skip this example. We proceed with the fourth examples here. We assume that we have same fiber in the previous example here, but now the DM is changed to 15 picosecond per nanometer per kilometer at a wavelength of 1550 nanometer. Okay, now we can say that we have different lambda used, which is 1550, and as a result, your DM will also different, yeah, which is at 15 picoseconds per nanometer kilometer. Okay, and now there's a change whereby the laser source is 0.2 nanometer spectral width at a wavelength of 1550 nanometer. So the question is, what should be the RMS pulse broadening per kilometer due to material dispersion in this case? Okay, all right. So again, basically the third and the fourth questions here is for us to understand what should be the effect on your spectral width, yeah, to the value of pulse broadening or pulse spreading. So as what we have learned in the previous slide, earlier slides of this lecture 6 part 2, we have learned that if we have reduced spectral width, yeah, if you have reduced spectral width, by right the pulse spreading will also be reduced, yeah, because from the equation itself we know that the pulse spreading is proportional to this spectral line width. Yeah, so basically if your spectral line width is increased, then your pulse spreading will also increase, and vice versa. Okay, so I don't think I have to proceed with this. So basically third and fourth question is just to show you what should be the effect when we have a smaller spectral line width. So basically the effect will be a smaller pulse spreading will be recorded. Yeah. Okay, so let us proceed with these examples. We have to estimate the RMS pulse broadening per kilometer for the fiber in the previous examples when the optical source used is an injection laser. All right. Okay. Right. So we are given these problems here. Need to find the RMS pulse broadening. We are given this condition. Delta lambda over lambda, which is 0.0012 at this wavelength of 0.85. So in order for us to find the RMS pulse broadening, this is based on this equation, yeah. We know that the DM, yeah, the DM is to be based on, okay, we can choose any one of these. So let's say we choose this one. Yeah, we choose this one. And from this example just now, we have obtained the DM, right? We have obtained the DM. So the DM is not mistaken, is about 98.1 picosecond per nanometer per kilometer. So we have to use the dm, which is 98.1. Okay, substitute in this equation. The sigma lambda can be obtained straight away because we know that from this equation, sigma lambda over lambda is 0.0012. So to find the sigma lambda, simply we just multiply 0.0012 with this 0.85 micrometer. So that will give us the sigma lambda. And by substituting this equation here, straight away we can find the sigma m. Okay. Okay, now I'm going to show you this solution to make it clearer for us. Yeah, it's nothing much there, just a substitution of value. Okay, so this is for the previous case just now. Yeah, okay, you can read this on your own. Okay, this is the one that I mentioned just now, which is the sigma lambda over lambda is 0.0012 at this wavelength. So from this equation, we can straight away find out the sigma lambda, which is the RMS spectral width, which is multiplication of 0.0012 with the wavelength, which will give us 1.02 normeter spectral width RMS. Yeah. Okay. So from this equation, we use the dm, which is 98.1. So the RMS pulse spreading per kilometer will be simply 98.1 multiplied with 1.02. So finally, it will be 100 picosecond per kilometer. Yeah, it's very straightforward lah. Yeah. Okay, so let's have a look at this example, the last one for material dispersion. We have a silica. Okay, we have a silica then. Silica single mode optical fiber cable, which is used to connect 2 points of 100 kilometer distance. Okay. The light source used at 1550 nanometer has RMS spectral width of delta lambda nanometer. Okay, yeah. So information given is that we are having silica single mode optical fiber. The distance of fiber, the optical length is 100 kilometer. The light source wavelength is 1550 nanometer, and the RMS spectral width is the delta lambda nanometer. So first question is estimate the value of delta lambda if maximum bit rate of the link is 100 megabit per second. Okay, number one, yeah. Estimate the value of delta lambda if maximum bit rate of the link is 100 megabit per second. Number B, part 2, if the link was intended for higher bit rate of 600 megabit per second, estimate the spectral width of light source that will be required. Okay, so this question is quite challenging. Yeah, we need to understand the concept clearly, this particular case. Okay, so we are given a single mode fiber, which is a silica base, yeah, because and we are given a distance of 100 kilometer, light source is 1550, and the RMS width, spectral width is delta lambda. Okay, we need to obtain what should be the delta lambda if maximum bit rate of the link is 100 megabit per second. Okay, so looking at these questions, we need to actually know the information given here. Yeah, what is the purpose of giving us the maximum bit rate of the link here? What is the purpose of this maximum bit rate of the link? Okay, so we just recall back the thing that we have learned in lecture 6 part 1. Yeah, remember we have learned about this intermodal dispersion, and there is one slide, if I can recall back, that give us the bit rate value, which can be calculated based on the value of a dispersion. Am I right? We have two values of bit rate. The first one, when we consider no overlapping conditions of the pulse. Yeah, if you can recall back, the BT, bit rate is a BT, yeah, BT is 1/2 delta tau. And if we have a RMS case, your BT is 0.2 divided by sigma. Am I right? Yeah, 0.2 divided by sigma. Yeah, you can recall that. You can refer to lecture 6 part 1. Okay, so in this particular case, we are referring to the RMS value, yeah, because in the question given that the RMS spectral width of delta lambda. So basically, you have to consider that the pulse spreading value should be RMS value. So the bit rate that shall be used, yeah, the bit rate equation that shall be used should be related to the bit rate that can be calculated by using the value of RMS pulse spreading, which is 0.2 over sigma, yeah, 0.2 over sigma. So the sigma here will be the pulse spreading which is due to material dispersion. Why? Because we are having here a single mode optical fiber. So we have learned that in a single mode optical fiber, we have a dispersion effect, but there should be no intermodal dispersion exists in your single mode, yeah, because we have learned before this that intermodal dispersion only exists in multi-mode optical fiber. So in this single mode optical fiber, the dispersion that you're going to get is your material dispersion. So from this maximum period that we're going to get, the sigma that we are going to get is the sigma due to material dispersion. Yeah. So from this sigma, we can use it to find the spectral width, provided that we know the value of dm. Yeah, provided that we know the value of dm. So how can we know the value of dm? The value of dm can be obtained because this is a silica fiber. So for silica fiber, we can use a special equation to calculate the dm, right? Okay, so to make it clearer, let's have a look at the solution. This example, yeah. Okay, right. So this is the one, the solution. So we know that the silica single mode fiber, the L is 100 kilometer and the lambda is 1550 nanometer. So this is what I meant just now. The BT, the bit rate is 100 megabit per second. So we need to adopt this equation, right? So I'm hoping that you still remember this equation. You have seen this in the previous lecture 6 part 1, which is for the case of intermodal dispersion, but still this equation can still be used, yeah, can still be used regardless of dispersion, whether it's intermodal, whether it's an intramodal, yeah, as long as we know the value of dispersion here, we can use it to find the bit rate, yeah. So we know that we are referring to the RMS value, so the bit rate should be based on this equation 0.2 over sigma. Okay, so for this, the sigma, which is the material pulse rate, RMS material pulse rate should be 0.2 divided by the BT, which is 100 megabit. So we're going to get the sigma will be 2 nanoseconds. So this should be the pulse rate, yeah? That should be the pulse rate of your fiber due to material dispersion. Okay. So I did mention here that due to single mode fiber, there should be no intermodal dispersion. Okay, and in this case, we assume negligible waveguide dispersion. Sorry, I have not covered the waveguide dispersion, but waveguide dispersion also exists in a single mode fiber. But in this case, we assume that waveguide dispersion can be ignored. Yeah, that's our assumption. So we can ignore the effect of waveguide dispersion. And for this, our assumption is the pulse spreading is totally due to material dispersions only. Okay, so from these assumptions, we can use this equation to find the dm. Okay, the dm is based on this equation for the silica-based fiber, where lambda zd, which is a zero dispersion wavelength, is 1276 nanometer, and the lambda that we are using in this example is 1550 nanometer. So we're substituting these two informations. You're going to get the dm is 21.56 picosecond per nanometer kilometer. So from this dm, you can substitute it into this equation, yeah, to find the sigma lambda or the spectral line width RMS value, in which the sigma m, which is this value, yeah, material pulse spreading, is 2 nanoseconds, equals to the dm multiplied by the length and multiplied by the sigma lambda. So end up, we're going to get the sigma lambda will be equals to 0.92 nanometer. So this is your RMS line width, yeah, RMS line width for this optical source at 1550 nanometer. Okay, so hopefully you understand the concept here clearly, yeah, on the calculation of line width in this case, yeah. Okay, now let's have a look at the second part of the question. So for second part of the question, it mentioned here that, okay, now the link was intended for higher bit rate. So we now increase the bit rate. Previously it's 100 megabit per second. So now it is 600 megabit per second. So for this increasing, or for this increment of the bit rate, what should be the new spectral width of the light source that will be required? Okay, yeah. So which means that now you're going to have a higher data rate transmission. So for higher data rate transmission, what should be the effect on the spectral width that shall be used in this application? Yeah. Okay, so again, for this bit rate value that we're going to get, what you have to do is you need to find out what should be the pulse spreading that is expected. Yeah, because from this bit rate, we can calculate the pulse spread, RMS pulse spread. So for this RMS pulse spread, we can use it to find the spectral width of the light source. Yeah. Okay, so the idea is the same as before. Okay, so let's have a look at the solution for this. Okay, so should be the case, yeah. Your BT is 600 megabit per second. So from this BT, you can calculate the new pulse spread RMS. So 0.2 over 600 megabit. So it should be now, the pulse spread has been reduced tremendously. Before this, it is 2 nanoseconds when we have 100 megabit per second data rate. But when we increase the data rate to 600 megabit per second, the pulse spread shall be reduced to 0.3 nanoseconds. So the pulse spread value is very small now, yeah. And as such, when we substitute this sigma into this equation, your line width RMS value shall be only 0.15 nanometer. So previously, we're going to have 0.92 if the data rate is 100 megabit per second. But when we increase the data rate, your spectral width must be reduced to 0.15 nanometer to cater for this high data rate transmission. Okay, so hopefully you understand now the effect of data rate, the effect of material dispersion, yeah, to this, and also the effect of line width to the material dispersion. So it's very important to understand this concept very well. Yeah. Okay. Any questions so far on material dispersion?
So far, okay, Doctor.
Okay. Yeah. Oh, all right. Very good. Hopefully you understand this clearly. Okay. So we're going to continue now with waveguide dispersion. Can we have a break for 5 minutes before we start with this topic?
Yes.
Okay, 5 minutes, yeah? Thank you.